Okay, I'm not quite sure what happened there, but good news is I got the first half of the lecture uploading, and the thing seems to be working again. So where we kind of left is got these rates of growth, which can work for any process. Again, it's a fight between two little driving force. And then down here, diffusion gets slow as you drop down. So that's where you always get these C curves from. Okay. So what I want to do the rest of this, as I've done in class, the only other thing that I really talked about in any depth was a little bit of nucleation, then run through a few, a little bit of stuff on age hardening, then went through a few bigger picture questions. So this is stuff you should have gone through before with Professor Wong and know these things. Again, these are some pictures we talked about of phase transformations in steels. Again, you get these structures. This would be a coarse perlite. This would be a fine perlite. And in both cases, a good question to ask yourself is what is the carbon content approximately each case? And you should answer it's about 0.8% carbon. That's fully perlitic, which means you had austenite that you'd quench down. And if you take these structures and hold them a long time, they want to decrease their surface energies. And so they form these things called spheriodite. And again, this is these lamellae end up basically breaking up, and diffusion brings them into spheres to reduce their surface energy. Usually, there's another picture in here that shows sizes. Usually this is on the order of a few microns, which is really actually fairly large in the whole scheme of things. And when we talk about things like precipitation hardening or dispersion hardening, usually those are in the order of tens of nanometers, not a few microns. So very different scales. Again, much bigger than atoms, which are at the other end of the scale. Again, here's the formation of martensite. This is where you just start forming martensite. You see shear transformations in these needle-like structures. If you were to draw a scribe across here, you'd see a shear that would take place across these. This is martensite. In the case of bainite, you also see cementite formation within that, and that's what you end up seeing in the bainite kind of structure. These are more pictures of those transformations. Again, most of the rest of this you've gone through. Another good question is these two. Can you estimate carbon contents on these? Again, this is about 50% ferrite, 50% perlite. Put it about there, about 0.4% carbon. This one here, this is clearly hyper-eutectoid. You're seeing carbide formation on the prior austenite boundaries. So this is probably something like about 1% carbon. About 1% carbon in that case. And then this one would be fully perlitic. So it would be about 0.8% carbon. Okay, the rest of this we've largely gone through. Again, you're seeing a whole diversity in structures you can get depending on cooling rate. This is coarse perlite, fine perlite, and here you see again going from coarse to fine. This is increasing cooling rate. Pen is giving me more than its share of trouble. So again, this is how perlite grows. You end up forming these plates of alternating plates of alpha and cementite out of the structure. We talked about as much as JMAC as we're going to. This is where the C curves come from. A lot of this is fairly redundant. Again, here is the formation of martensite out of out of out of out of austenite. Again, bainite kind of looks feathery. It's martensite. You get these transformational laths that form. Higher carbon content, higher the strength is. Also talked very briefly in class about continuous cooling curves. A slight transformation. Again, the typical TTT curves we end up doing. This is where you drop to a given temperature and hold for a given period of time. It's a very nice academic way of doing things, but very often you've got something like a big blob of steel and you let this thing cool at some kind of a rate, and usually you get temperature versus time does something like that and continuously cools. Well, you can retransform this where you can put temperature versus time on this way. So this would be a relatively fast cool. This would be relatively slower cool. And you end up getting different products. And again, you really can't get in the bainite bay this way because you have to drop and hold at these temperatures, and that doesn't work so well. So these continuous cooling diagrams also can be useful, and you can see based on this, if you can miss the nose, this is your critical cooling rate. If you do a water quench, you can get something that's fully martensitic. If you get something that's through here, you can get martensite and perlite. So part of the austenite transforms to martensite. The remainder is available for perlite. You're at a faster cooling rate, or a slower cooling rate. You see fine perlite, slower cooling rate, yet you see coarse perlite. And then mechanical properties of steel, we could talk about this for a long time, and we did not go through this in class either. Again, here's perlite, there's the formation of martensite. If you don't have enough time for carbon to move, you end up forming this martensitic structure, which can happen without diffusion. Okay, the last thing I wanted to end on was precipitation strengthening, and I just wanted to end on, I've talked about this in the prior lectures, including the last video lecture, but I wanted to put a very specific question on this for you, and that's the following, is typically, again, the way we do precipitation hardening, you have a phase diagram, might be a binary, very often it's a more complicated system, where this is %B, this is temperature. You have some kind of a system, looks something like this. The question I posed is, what we typically do is solutionize, quench, and then age. So what we do is, if we plot temperature versus time, we solutionize at this high temperature, quench to T low, and then age at some temperature T. So we end up doing is this. So we hold at a high temperature, we solutionize, we quench. Some time might sit there after it's quenched, and then we age for some period of time at the aging temperature. Okay, why do we do that? Why instead don't we do something instead that might look more like this, where we simply just find some kind of a nice programmed cooling rate and cool it down at that kind of a programmed rate? Why don't we do that? And give yourselves a moment to think about that question. Okay, so the reason we do it the way we do, and let me, before I say that, go into something else. So we often plot hardness as a function of time, so a logarithmic scale. Right after we quench, remember the four kinds of strengthening mechanisms Professor Wong talked about. You've got work hardening, you've got grain size strengthening, you've got precipitation hardening, and you have solid solution strengthening. And all these, work on very different length scales too. So if we plot hardness versus time, we typically see a curve that looks something like this. Where you can see this period is nucleation. Then we end up forming small shearable precipitates in here. So the precipitates that we form are small. And if a dislocation comes through on this glide plane, what ends up happening is it takes that particle and shears it like that. And eventually they get big enough so that the instead of this happening, the dislocations have to loop around it. Gives you a much higher strength. And then we eventually here reach peak hardness, where the particles get large enough to resist the dislocations. And then, like we talked about before, things want to reduce their overall surface energy. So what happens is you have a process here of coarsening, and small particles get eaten up to form big ones. And through this, your yield strength, you probably got this from Professor Wong, the yield strength goes as UB over lambda, where mu is shear modulus, B is the Berger's vector of the dislocation, and lambda is this interparticle spacing. Okay, so back to the big question. Why do we not do that? Why don't we just cool at a specific rate? Well, big reason is, remember what we talked about is when we cool at some kind of programmed rate, we tend to favor heterogeneous nucleation at some peak here. So our maximum rate of heterogeneous nucleation might be here. Our maximum rate of homogeneous nucleation might be down here. And there's homogeneous nucleation down here. What is heterogeneous? What does heterogeneous nucleation mean in this context? Well, in that context, what heterogeneous nucleation would mean basically precipitating out the beta phase on grain boundaries. Is that a good thing? No, for two reasons. Number one, you waste your alloying elements putting them on the grain boundaries. Secondly, you may end up embrittling your material by putting forming large intermetallics along the grain boundaries, giving yourselves a brittle path. So that kind of hopefully puts a little bit of a bow onto this idea of precipitation hardening. Precipitation hardening is using these nucleation phenomena, and in particular what we end up doing is favoring homogeneous nucleation over heterogeneous nucleation to give you a very fine dispersion, so you can minimize the spacing between particles that are big enough to stop dislocations. And if we can do that, we minimize this, we make our strength large. Okay, that's it. I'm going to end kind of the formal part there. I did talk a little bit about some possible questions in class that I'll bring you up to date on. So first of all, really good questions in oral exams and things like this are things like, imagine you're going to cool through some kind of a temperature range like this. Describe what happens with respect to the phase rule and microstructure development. That's something that you all should be able to do. Second question I asked in class is why are ceramics brittle and metals ductile? Give yourself a second to think about it. You should, as somebody who's a materials neophyte, be able to start answering that. And remember, in this class we talked a lot about dislocation motion, and when we try to make strong materials we try to inhibit dislocation motion, but we still like to have some dislocation motion. And basic reason is we know that all materials have flaws. If you've got a material that has a little flaw in it under tension, one of a couple of things might happen. if that stress is big enough. So one of the things that might happen is you blow this up, you can end up having this crack here, and you've got interatomic bonds here, and that stress can basically start rupturing these intraatomic bonds. That's one possibility. The other thing that might happen is you might have this, and you might imagine that there's a dislocation slip plane that moves through here like this. Dislocation could move through, and the action of that dislocation could actually move this out to start blunting that crack out like that. So this would be one Berger's vector. It can do that again. Do that again, and eventually take this and blunt that crack tip out. And if you blunt that out, that's the way we make materials ductile. So the main reason ceramics are brittle and metals are ductile is dislocation motion can dissipate that energy in metals. Another question: how do we strengthen metals? I think Professor Wong talked at some depth to you guys about that, and basically we've got a number of mechanisms we talked about: work hardening, solid solution strengthening, grain size strengthening, and precipitation hardening. Again, you should all be cognizant of what kind of length scales are involved in each case. In the case of solid solution strengthening, you're dealing at an atomic scale. For things like grain boundaries, grain sizes might be 10 microns, which is a whole lot of atoms, and you should be able to do that computation. Okay, I'm going to stop there. It's been my pleasure being with you this semester, and good luck on the final. Please ask any questions you might have over email, and we'll take care of them best we can. Let's see if I can gracefully get out of this thing. Okay, got to connect the keyboard maybe.